So where did we get to? Before the break, we said that we can build something that lets us estimate the quantity that we want, that meets the kind of inequality that we want, but only with constant probability. And we'd like some way of amplifying this from constant probability to arbitrarily close to 1 probability. So reduce the probability of failure down to delta, which is much smaller. Okay, so we're going to create the Chernoff bound. And I'm going to do this fairly quickly so we can get through it. So I'll just sort of show you the gist of what we're doing. So what's happening is I can do this process on the previous slide once, and I'll get something that has the right property with constant probability. So I'll now look at what are some properties of if I do multiple trials, each of which succeed with constant probability. So new set of random variables, x1 through xm, independent Bernoulli trials, so each one succeeds with some same probability p, fails with probability 1 minus p. Right? So it corresponds to, well, I don't know, succeed or fail, just is 1 with p, 0 with 1 minus p. So let me now analyze, how much do I deviate from expectation when I can treat each of these as independent. So let me look at, well, just what's the sum of the values that I see based on m independent draws. I know that the expectation, what I expect is m times p, right? That's the expected value of this sum. Oof. So here's what you get. You get a horrible long line of algebra on one slide. So what are we doing? We're saying, well, what I'm interested in is understanding this one-sided bound. So one-sided bound is what's the probability that this x, some of these independent trials, is more than its expectation by a relatively small amount, by a 1 plus epsilon factor. Okay. So again, we're going to use Markov inequality again. There's no big surprise there. So before we applied Markov inequality directly, we applied it to the square of a variable. Now we can apply it to some weird-looking function. We'll take the function that's e to the power t times its variable. So note that e to the power t times something preserves this inequality. So if x is greater than 1 plus epsilon times its mean, then e to the power t times x is greater than e to the power t times 1 plus epsilon times its mean. And then we apply, once we've done this transformation, so these two things are the same, we just manipulated, then we just apply Markov inequality, and it says what we're interested in now is looking at what's the expectation of e times t to the x. Right? And this is just some constant. So far I haven't fixed t, I'll fix t at the end of the analysis. So the rest of this proof is basically about saying, how does this behave? What's the expectation of e times t to the x? That's an expectation of something which has at its heart a sum, but once I take that sum sort of outside of the exponential function, that becomes a product. So I can think of it as a product of expectations of the independent individual xi's. And these only take two possible values, one with probability p, 0 with probability 1 minus p, so I can actually just explicitly write out what is that expectation. It's this product over all the different variables, so over the m variables, of 1 minus p times what you get when you put a 0 in here, which is a 1, and a p times what you get when you put a 1 in here, which is e to the power t. Okay. Then the rest of the proof is just a bit of algebraic manipulation, so you can prove quite a few different Chernoff bounds based on what kind of bounding functions you like to do to exponential functions of this form. Using fairly rudimentary tools, you can just sort of manipulate a bit and modify, rewrite this, and say that this expectation is equal to the exponential of mu times e to the t minus 1, or is bounded, upper bounded by. Okay. So if I go back to something in the middle of this line of algebra, right, I've got this equation here, this probability, or rather this one, is less than or equal to this expectation, drop it down in there, divided by this e to the t times 1 plus epsilon mu, that goes in there, And I sort of expand out the exponential function of this e to the t. And then it's just a question of, well, what will I choose? How will I choose t to kind of bound this term in here? So sort of stick a finger in the wind and say, if I pick t to be something like 2 epsilon over 5, then for a small enough value of epsilon, smaller than 4, when I plug that in here, this expression is bounded by e to the minus mu times epsilon squared over 4. Okay. So what do you take away from this exercise in algebra? You sort of take away this part, that the probability that this sum of m random variables, m independent Bernoulli random variables being more than a 1 plus epsilon factor of what you expect, decays quite quickly, decays exponentially fast in terms of depending on mu, but also primarily depending on epsilon squared. Okay. So note that this kind of concentration inequality, it's much stronger than the ones we've seen before. It's much tighter than Markov and much tighter than Chebyshev, but it relied on the fact we were looking at a particular kind of random variable. We were looking at Bernoulli trials, and we were looking at the fact that they were independent. Right? You can get quite similar forms that look at different kinds of random variables, but still require them to be independent. Right? But this is the one that I want for today. Okay. So sort of go back to what we said. We've got estimates coming from the sketch. Each estimate is good with constant probability, good meaning it's sort of fairly close. And what we do is we take all of those repetitions, those d repetitions, and we take the median of those. So why are we taking the median of those repetitions? So think about, I'm going to do this very graphically, think about my estimates laid out in a line from smallest to largest. And I'm taking the median, which is sort of the one that happens to fall in this middle location. So now think about some of these estimates are bad, right? They're bad in the sense that they are outside of my desired bound, right? They're more than some epsilon away from the true value. But because I've laid them out in sorted orders, either if it's bad, it's because it's too small, or it's bad because it's too big, right? So the only way that I could get an overall estimate when I take the median that's also bad is if there's so many bad estimates that it kind of overwhelms me. So, I've got these sort of bad estimates that are too small to the left, bad estimates that are too large to the right. Unless I'm very unlucky, the median should be good, right? So what's the minimum criterion for the median being bad? It's that at least half these estimates must be bad. Okay. Well, I carefully chose my probability so that the probability of getting a good estimate was at least 3/4. So the probability of a bad estimate is at most 1/4. So I expect only 1/4 of these to be bad. And my final estimate is bad if more than half are bad. Right? So now I can plug in that Chernoff bound that I've just built. Right? So I've got d-independent estimates that are each bad with probability of 1/4. I'm looking at what's the probability that I see more than twice what I expect. Right? So I plug in that result, and basically, I'm putting in a constant epsilon in the previous bound. So it just depends on 2 to the e to the minus d over 4 or d over 2 or something. The main thing is we've got this sort of exponentially small dependence that decays as a linear function of d. So d is my number of repetitions, so I just increase d to drive down this probability essentially as small as I like. I get a similar thing to what I got with the other sketches, right? I got this thing that says I can make, if I want a particular delta probability of failure of the overall estimation procedure, I just need something that looks logarithmic in 1 over delta. Okay. So this applies to this particular construction, but it also applies to a huge bunch of other constructions that people have used in sketching and summaries, right? This idea of basically you have to get things to the point where you've got a constant probability of a particular estimator doing what you want, and then you use something like Chernoff bound in a fairly automated way a lot of the time, just to get that constant probability down to arbitrarily small probability by doing some fairly cheap number of repetitions. Okay. So what does this give you? This gives you a way of estimating the norm of vector, the Euclidean norm of a vector, of this frequency vector. So I can directly estimate the sum of the squares of the frequency vector. So I can just take the square root of that estimate and rescale a bit, and I also get an estimate of just the direct Euclidean length. Right. The cost is primarily driven by the width, the number of buckets that I need, so that looks like 1 over epsilon squared. And that gives me a relative error guarantee. So my error is only an epsilon fraction, say 1% stretch or shrinkage. What else can I do? I can do inner products. I can do inner products more directly, but without proving anything else, I could say I can do inner products because I can write an inner product between x and y in terms of a bunch of sum of squared of x individually, y individually, and x plus y. Right. So I can just sort of say, I'll build 3 sketches, one to estimate the squared norm of the sum, one to estimate the squared norm of x, one to estimate the squared norm of y, rearrange, and the error that I get is not what I'd want. I'd really like to be able to do this with error that looked proportional to the answer. But because this problem encodes the hard problem of disjointness, right, the dot product is sort of a generalization of testing if there is any intersection between 2 vectors, then I'm not going to get relative error. I have to get this sort of additive error term. If I want to estimate a particular entry, so I want to say, tell me an estimate of a particular entry of the original vector. So I can pick a new vector y that is this sort of elementary vector. So it's 0 everywhere except on coordinate j where it's 1. And I can use this dot product approach to estimate the inner product of the data vector x with something that's sort of an indicator at a particular location. That should be, the correct answer is the value that I want, and the error looks like epsilon times the 2 norm, the Euclidean norm of the data vector. So this lets you actually contrast. The previous sketch, the count-min sketch we saw first, gave you this with a 1 norm guarantee. This sketch gives it with a 2 norm guarantee, but with a higher cost, this had a space bound that looked like 1 over epsilon, this has a space bound that looked like 1 over epsilon squared. Actually, there's not too much difference between these sketches when you really get down to it. Right? They're both telling you accurate information about individual entries in the data vector. And if you want to connect this to the world of geometry and dimensionality reduction, you can see this as a sort of realization of the Johnson-Lindenstrauss lemma. Right, so the Johnson-Lindenstrauss lemma says that you can take a vector in high-dimensional Euclidean space and map it down to a much shorter vector in Euclidean space and preserve the norm. We're almost doing that here, except that we're not strictly mapping into Euclidean space because we've got this median operator in order to get our estimate. But we're doing so very sort of quickly, very sparsely. Right, there's bounds that say, here we're essentially, if you look at the sparsity, it has almost sort of constant sparsity. If I think about how much work do I have to do to process one index of the data vector, I'm just sort of hashing to a single bucket in each row. For Johnson-Lindenstrauss, I need to do something a little bit stronger in terms of how much independence I need. But it's all very much part of the same sort of landscape of dimensionality reduction. Okay. So let's move on and look at some other things we might do with sort of sketching kind of ideas. I'm going to look at F0. So F2 was this sort of sum of squares of frequencies. F0 is the number of distinct items, right? It's the number of elements that I see a non-zero number of times. And that's a fairly fundamental kind of thing, right? I want to know how many people have viewed a video on YouTube or visited my website or something, and I want to do this more compactly than just keeping a list of everyone who's been there. All right, so this was first looked at in the 1980s. I'll give us a sort of simple version that came out about 20 years after that, which is the k-minimum values algorithm. So the idea is reasonably clear. So think about my elements. So I've switched notation for about a third time now. I'm now drawing them from a universe of size 1 up to m. And what I'll do is I'll just use a hash function to remap elements down. So I'm being slightly nonlinear here. I kind of have to be nonlinear to do F0. But I'm still using hash functions. So I've got a hash function that takes each element from my input space and maps it onto some new space. And I'm just going to make this new space larger. So this is actually going to spread things out in contrast to the previous results which made things collide. All right, so I'm going to map onto a much larger domain so that I can effectively say the chance of a hash collision is negligible. Right. So what do? I'm going to track information about how the elements in my input map into this hashed space. Right. So for each element that arrives, compute its hashed value under this hash function h. And rather than tracking all of them, I'm just going to track a subset of them. I'm going to track some number t of distinct items that achieve the smallest values of this hash function. So some element comes along, and I immediately map it into this space, sort of 0 up to r. Right. Another element comes along. So I'm going to track the simple case for t equals 2. So I'm tracking, the two elements with the smallest hash values. So sort of in this range, I'm keeping information. Up here, I'm ignoring what's happening. So now if I see sort of the same thing happen, right, so then I get another element, move down, I'm just looking at the top, the two smallest hash values. If I see the same element a couple of times, or if I see elements up here, I can just ignore it, right? So I saw that green one again, doesn't matter. It's the same, but this yellow one comes along, and now I'm just looking at, here's the two elements that achieve the two smallest hash values. More items come and I ignore them. So how do I get from this to some estimate of how many different elements have I seen? I'm basically going to use a sort of a uniformity argument. I'm going to say, well, I was keeping information about t elements, and the t smallest hash values occupied, this fraction of the whole hash space. So I'm going to assume things sort of were fairly uniform outside what I observed. So if I saw two elements in this fraction, I can just sort of take the reciprocal of that and scale up to say I expect on that basis that I saw this many elements in the whole domain. Right? So you can sort of work out what that extrapolation would look like, and it basically says take t over this value of the hash function of the t smallest, in this case the second smallest, and multiply that up by r. Right? So you can see this term r over vt, the reciprocal of that vt over r is roughly the fraction of the domain occupied by those t smallest elements. So how do you analyze this? How do you say that this is going to give you a good estimate for the quantity that you want, the number of distinct elements? So f0, I'm going to write that as n just to save a bit of space as I go through. So what you do is you say, well, just what's the chance of getting a bad estimate, right? Same kind of approach as we did before. What's the probability that my estimate in this case is too high, right? So my estimate is too high. If you sort of think through the process, my estimate is too high if this value vt is too small, because the way it goes into the estimate is sort of reciprocally, right? So I should have, if I put the right value in, the right value of n in, I should have seen this value for my hash of the t smallest values, or I should have seen something no less than this. But I actually saw something smaller because I saw too many items that hashed to a small value. Right. So basically, what happens is the number of elements that hash below a particular threshold value as a function of the true answer was too many. So it's important to sort of view it in these terms, because I can then take that event, that there were too many elements hashing to a small value, and break that up into events on a per item basis. Right? So I do a little bit of, try not to get, I'm actually going to sort of not go too detailed through the notation here, so try not to get sort of too hung up on the notation, the little bit of algebraic manipulation. The key thing is just to say, rather than look at this as sort of an event that involved a lot of elements, I can say this is an event formed by individual elements collectively, right? So I can look at a single element and say, what's the probability it fell into this range, right? And that's that depends on this hash function. The hash function is operating fairly uniformly on an individual element. So I can basically say the probability that an individual element hashes sort of below this cutoff threshold, I can write, roughly in terms of T, this, which is what I base the threshold on, N, which is the total number of distinct elements, and 1 minus epsilon over 2. Right. So I've chosen my parameters in such a way that I can look at this probability that an individual element hashes too small. Again, don't get too hung up on the analysis. We've done a bit of rounding as well. So I can now say, well, how many do I expect? Right. So I know the probability the particular element hashes into this range. And what I'm really saying is that I'm going to see more than I expect hashing into this range. So I'm going to do the same kind of expectation variance kind of analysis. So let y be the number of elements hashing in this range. I know the expectation isn't too many. Right, so I expect to see sort of 1 minus epsilon over 2t. And I can look at the variance of this event, right? Again, we're dealing with just a single, essentially Bernoulli event with a fixed probability. So the variance of this quantity is just the sum of the variances corresponding to each individual element. I can sum variances because I don't need a very strong independence to sum variances, right? All I need to say is that the variables corresponding to each element being hashed, I can treat as pairwise independent, so I can sum the variances. So I can look at what's the variance of this number of elements hashing in this range, and it's basically bounded by this quantity, 1 minus epsilon over 2t, which in turn I'll just say is just smaller than t. So I'm dealing with a variance that I understand. And what I care about is, I expected not too many. I expected slightly less than t elements to hash. My bad event, which I get a too large estimate, is basically because I get too many elements, so more than t elements, achieving that value. So I just kind of plug this into the Chebyshev inequality. So it's saying what's the probability that the number I observe is more than its expectation by more than an epsilon over 2. Additive quantity, plug some things in. And what I get out is that this depends on t. So remember, t is just how many elements am I keeping track of, right? So in my original example, I was keeping track of 1 or 2. If I keep track of 2 elements, I'm going to have quite a lot of uncertainty. So obviously I increase the number of elements, and that hopefully gives me more certainty. And what this says is if I set t, the number of elements that I'm keeping track of, to look like 1 over epsilon squared, then the probability for one instance of this algorithm that I get an estimate that's too large is at most a constant, right, is a fifth, plugging all this through. So it's just basically sort of figuring out what's the right event to analyze and applying the right concentration bound to that event. Right. So that says that the probability that I get a large estimate is not too high. More or less symmetrically, you can look at the other side and you can show the probability that you get an estimate that's too small is bounded by another constant. So by a union bound, there's a good chance, more than half, that any particular run of this algorithm gives me a good estimate. So then what do? I do that outline that I just showed a few slides ago. I'll repeat this a few times in parallel and take the median of the estimates. Right? And again, I'm good with constant probability, so things go wrong if many more independent runs go wrong, and that the Chernoff bound squeezes that very quickly. It's exponentially unlikely to happen very often. Okay. So what you get is you're keeping track of t hash values. So naively, you're taking something that looks like t, which is 1 over epsilon squared, times the size of the hash value, which is log m. You can squeeze this down by some more hashing tricks and bit representation tricks that I can't remember the details of, to get this more like additive log m. Yes?
The plus log m version isn't in the bodies of paper,
I
right?
think it is. Some version is.
Okay.
Because this, I've kind of given you sort of algorithm 1 from the 3 algorithms, and they do sort of 2 and 3.
But isn't this thing what Jelani and others did?
No, it's David and Jelani, and I forget if that was one of the David Kane papers as well.
There's
Kane, Nelson, Woodruff. They were looking at the slightly more general version with, I think, additions and deletions, if I remember correctly. And they had to do sort of a bit of chaining, a bit of stable distributions to tell them where to look and other stuff. So there's more. The summary of that cryptic conversation is there's a lot more complicated stuff you can do for this problem to really sort of squeeze the bit complexity down to the optimum. So I'm kind of there's probably that may well be an O tilde, but what's an O tilde between friends? So the space is pretty good, and the time cost is also good because every time you do an update, every time you see a new observation, you hash that element. That's fairly quick. See where it lies. If it's small, then you've got some priority queue of your smallest elements, so you can make this all pretty fast. Okay. So I'll just say a quick word about how this gets used in practice. Because people do often quite want to count lots of things compactly. So actually, it was work by Flageolet that sort of engineered a good thing, and then that's been engineered further by people at Google and elsewhere to actually really implement this. So they used additional tricks based on hashing, where you hash each element to one of a number of different buckets, and in each bucket you run a version of this algorithm. But instead of actually keeping the t smallest elements, you just look at the one smallest element, and you don't even track what that one smallest element is. You just track some, which is the most significant bit of its hash value, right? So each one of these individually is very noisy, but because you're sort of splitting your input over a large number of buckets and doing a more complex sort of hypergeometric averaging of those estimates, then what you get out the end of it is rather more accurate. And people like it because they don't have to understand the analysis to use it, but to implement it is very easy because keeping track of this maximum value of the logarithm of the hash function is basically you're keeping track of 5 or 6 bits because there's only 5 or 6, there's only 30 or 60 possible values that this index can take on, this most significant bit value. And you can do some tricks with this. So you can do things like, you can estimate the size of the intersection. Again, you're only going to get this estimate of intersection size up to some additive approximation factor, right? So you can say, how do I estimate the size of the intersection of 2 sets? Well, I can just estimate the size of each set individually, then subtract my estimate of the size of the union. Estimating size of unions is fairly straightforward using these things because either in this version or in the K-min and value version, you're just sort of you've got all the information you need to say what would my sketch look like if I had seen the concatenation of these 2 streams. Right. But your error scales something proportional to square root the product of the size of these 2 cardinalities. So when this intersection is small, it gets kind of lost in the noise. And you can't hope for anything better than that. So I had a few more slides on this. I'm going to skip these over in the hope of saying something a bit different. Okay, so what have we done? We've looked at sketching, we've looked at sort of heavy hitters, frequent items, Euclidean norms, count distinct. And I'm going to look at sampling using sketches. Right. So again, we're seeing an input distribution in this general case where we may have positive and negative values. We want to sample elements based on the frequency distribution. So what's the kind of sampling I might want to do? I might want to just sample from the support set, so sample from the elements that occur with non-zero frequency. Might want to sample proportional to the weights or proportional to, let's say, the square of the weights. So how do you do this? You essentially use these sketching ideas in a sort of a compositional manner to build techniques that let you do this sampling. Right. Right. So the general form is this idea of LP sampling that says I want to sample roughly proportional to, what is the contribution of item I to the pth frequency moment, right? So, if p is 2, what's the squared contribution of I to the sum of the squares? Right. So I'll just talk about L0 sampling. So L0 sampling says I want to sample proportional to the 0th power. So in other words, I just want to sample from the elements that actually occurred, right? From the elements with non-zero frequency. And the general approach, sort of outlined about 10 years ago and then refined subsequently to that, goes roughly as follows. It says, well, when I see an element arriving, I'm going to sort of choose a sampling. I'm going to sample it with some probability into a new vector. So with probability p, I pass the element that arrives as a function of its identity, so as a function of I. With probability 1 minus p, I drop it. Okay. So that subsampled vector of frequencies, I then feed into another kind of data structure, which I'll explain in a moment, which is called a k-sparse recovery data structure, that basically says if this vector is sufficiently sparse, if it has at most k non-zero frequencies, I can recover that vector exactly. But if it's more dense, if it has lots of non-zero frequencies, then I won't be able to recover it. Okay. So if this subsampled vector, which I'm calling f sub p, is k-sparse, then I recover it, I sample from that reconstructed vector. How do I know what value of p to choose? So this is going to work if I happen to know roughly what the number of distinct elements is going to be. Well, what do? I do that old computer science trick of just making a lot of guesses in parallel. So I'm going to run this with probability p equals 1, and in parallel I'll run it with probability p equals half, p equals a quarter, and so on. Right? So for some high values of p, this is going to fail because this subsampled vector will still be too dense. With some small values of p, this is going to fail because the number of elements with non-zero frequency that pass this test will be 0. But there should be a sweet spot in the middle where I have a value of p that's about right, that thins out my input vector to be sparsity between 1 and k, and I'll be able to recover it. Okay. So it's always much simpler if I just put the picture up, right? So here's the picture. It says, here's my input represented by a collection of colored dots of different elements. I'm sampling with probability 1 down here, with probability much smaller up here. And so, as I pick different values of p, I get different densities. Feed each of these into this k-sparse recovery algorithm. For someone, I'll succeed. I recover that set that was sampled, and from them I sample an individual element. Okay. So there's a few bits to the analysis of this. One bit is just saying that there's a good chance that there'll be some element where this process succeeds. Right, so we're sort of in this Goldilocks thing, not too dense, not too sparse, but just right, somewhere in the middle. That's again, it's going to be a sort of a Chernoff bound to say that the probability of sampling works out. How do I do this sort of magic thing in the middle that says if you give me a vector that's mostly sparse, I'll be able to retrieve it? If you think about some of the sketching techniques we've used, if you apply a sketching technique to a sparse vector and then start querying for each individual element, x1, x2, x3, you can modify the analysis and say there's a good chance you'll actually recover the vector correctly. Right? It's a bit slow. So again, it's sort of in this realm of compressed sensing that you're sort of somehow recovering a vector that happens to be, a few spikes and zero everywhere else. So there's a bunch of ideas that have been proposed since then to improve on that. The kind of idea that works well in this scenario, sometimes being called invertible Bloom lookup table, uses a few sort of encoding tricks to say what I'll do is I'll sort of map elements again out to cells based on a hash function. In each cell, I'll keep information about the sum of the item identifiers and the count. I think there should probably be an I in there somewhere as well. But anyway, the sum and the count of the item identifiers and some fingerprint like that fingerprint we did at the very start. With the idea that if you have an element that maps into a cell on its own and nothing collides with it, you can use this information to decode the item identifier. Right? And if you find that item once, you can sort of take that out, figure out all the other places where it was mapped to in the sketch, remove those occurrences and keep iterating. Right? So that's called peeling. So that gets you a slightly better bound, and it means you can do this sort of reconstruction quite quickly. Okay. So that's sparse recovery in the slide. There's another thing to argue uniformity. I'll skip that. Okay. So what does that give you? That gives you a construction that lets you sample uniformly or almost uniformly from the support set of a vector. So I'll give, this is basically a teaser for Andrew McGregor's talk, because I think he's going to cover this in much more depth next week. But I'll sort of give you a teaser for that, which is how you can use this to do something interesting with graphs. Right. So the first kind of thing I might want to do with a graph, so far we've been looking primarily at data that I think of as representing vectors, but actually I can also think of data that represents a graph, just seeing edges arriving. So I see a whole bunch of edges and I want to know, well, is this graph connected? Or, how many different connected components are there? So if I were doing this, without any constraints, the kind of algorithm I might think of is to say, well, start off imagining that every node exists in a separate component, pick some edges that connect components, collapse those edges, notionally merge those components, and keep going until I can't collapse anymore. Right. And when I've done that, I've found all the connected components. So how might I do that in this sort of sampling small space world? I'd say, well, I can use this construction I've just built. I can use this kind of sampling algorithm on the stream of edges to allow me to sample edges from something that represents the adjacencies of each node and compact and use that to tell me, what's connected. So where this breaks is that if I think of applying this just directly, then it works, it begins going well, but then after I've done a few collapses, I've done a few iterations of this process, I'm much more likely to sample an edge that connects two nodes that I already believe to be in the same component. Right? So if I'm just uniformly sampling over edges, I'm not going to gain any new information if I keep sort of sampling directly from this sort of a vector of adjacencies. So Sediptu, over there, and Kukchin Arn and Andrew McGregor came up with a very neat idea, which was essentially an encoding trick. I'll give you the flavour of the encoding trick and leave it to Andrew and Sediptu to kind of fill in the details later. Which is that if I think of seeing an edge arrive, I can encode that edge in two places. I'm going to keep information on every node. I can encode the edge in two places. The edge ij is encoded once associated with node I and once associated with node j. And I'm going to encode it as sort of a weight +1 in one location and -1 in the other location. Okay. So if I determine that node I and j happen to be in the same component, I've got an L0 sketch for the adjacency vector of node I and an L0 sketch for the adjacency vector of node j. I'm going to sum those sketches together, right? And so my +1 and my -1 for that edge ij cancel out exactly and give me a net contribution of 0. Right. So at any point, what I do is I take sketches for nodes, combine them to get, here's a sketch that corresponds to my current connected components. All the internal edges have cancelled out, and so from each sketch of a connected component, when I do an L0 sample, I only draw from outgoing edges that aren't internal, that haven't cancelled. So I can build this into one big algorithm that lets me sample and draw out information about the whole connectivity aspect of this graph. Okay, so what do I do? What's the overall cost? I'm essentially running a parallel algorithm that's running in some number of rounds that looks logarithmic in the number of nodes. I'm keeping some space per node, but the amount of space per node is essentially one of these L0 sketches, so it's only polylogarithmic space per node to answer this kind of question. Once you can do this, you can start thinking about a whole bunch of other graph questions. Okay. So I'm now in the happy position that every speaker loves, which is to skip over a very large number of slides. So I want to sort of wrap up at this point. So we looked at quite a lot of different techniques, maybe more than you'd think. So we looked at how do you test vector equality using fingerprints, how do we look at estimating frequencies using count min and count sketch. We looked at Euclidean norm and inner products using the AMS sketch. We looked at count distinct using k-min and values and hyperlog-log. We looked at L0 sampling for hashing, via hashing and sparse recovery, which gave us graph sketching. And we just, in the 10 seconds where I skipped through slides, went over L2 sampling, high frequency moments, and linear algebra and matrix sketches. So from this sort of set of techniques, there's actually a huge set of problems you can tackle, starting off with things that are based sort of fairly directly on properties of vectors, but building from them to properties of graphs, matrices, and other higher order objects. So where is this world going now? We'll hear more of it over the course of this week and next week. But generally speaking, people are looking at, how do you extract sparse representation of high-dimensional objects? So I alluded to compressed sensing a few times, also work on sort of sparse, fast Fourier transformations. How do you take these things that work for vectors and apply them to more general linear algebraic computations? So now think of your data as representing not a vector, but a matrix or a collection of matrices. And you want to solve problems that look like linear regression or matrix factorization or extracting eigenvalues from those approximate representations. I mentioned very briefly graphs, so you talked a little bit about how you might find connected components. The other kind of things that are attracting a lot of attention at the moment is trying to identify matchings on graphs, looking for sort of clustering, finding dense connected clusters on graphs as well. You can think about what happens when your data is more geometric in nature and you want to solve all those kind of geometric kind of questions, clustering of facility location kind of questions, solving optimization problems when the data is so big that it's essentially encoding an optimization problem that you can't write down all the constraints for. And I sort of gave you a view of the world where we were seeing data in one location, but actually in the real world, your data is often spread out. At the very start, I sort of hinted that because of linearity properties, these kind of sketching ideas give you a foothold into doing distributed computation. because I can compute a sketch on this machine, I can compute a sketch on this machine, and at an appropriate moment I can bring those sketches together, sum them, and get a sketch of the union of the data that they've seen. But then sort of fitting that into various computation models like MapReduce or like other kind of distributed streaming models means you have to sort of put additional wrappers of algorithmic work around that. Okay, so here is a rogues gallery of sort of related topics. So tomorrow, David Woodruff will talk about heavy hitters. At the end of the week, Alex Andoni will talk about how sketching relates to ideas for embeddings. Hopefully next week, Andrew will be here to talk about graph sketching. And next Tuesday afternoon, Jelani will be here to sort of start addressing some of these matrix computational questions. Okay, so I'll end with a very quick advert. We are hiring on topics related to this and far beyond for PhD students, postdoc students, assistant professors, associate professors, and full professors. Thanks to all the wonderful sponsors that give me money so I can come to Paris in the spring. All right, and that's it. Thank you very much.